This is the third video on chapter 33, derivatives and graphs. And so here we have another rational function. F of x is x squared plus x plus 1 divided by x. In the last video I mentioned I like to write the function in as many useful ways as possible. So we can write it as x plus 1 over x. There's a couple advantages to that. And also I wrote it yet a third way down here. So we write it like this. This makes it easy to read off the oblique asymptote. The oblique asymptote is just x plus 1. Remember, if you have a rational function, the degree of the numerator is exactly 1 more than the degree of the denominator, you have an oblique asymptote. Writing it like this, as x gets large or small, as x tends to either infinity or negative infinity, this term goes to 0. So this function starts to look like x plus 1. So this function is x plus 1 plus a little piece or minus a little piece. So it eventually looks like x plus 1. So we have the oblique asymptote. Remember, with rational functions, oblique asymptotes and horizontal asymptotes are mutually exclusive. You can't have both. You don't have to have either one, but you can't have both for a rational function. Vertical asymptote, the vertical line x equal to 0. 0 is a root in the denominator, but not the numerator. It's neither even nor odd. See the notes for that explanation. Now, writing the function like this, x plus 1 plus x to the negative 1. In the notes, I differentiated this using the quotient rule, and there's nothing wrong with that. But it's a little bit faster if we write our function like this and then just use the power rule. So we take the derivative of the function. We have derivative of x is 1, derivative of 1 is 0. So we just have 1 plus 0 plus, and then we use the power rule. So we have negative 1 x to the negative 2. It simplifies to this, and we factor the numerator, and we make our sign chart. Now, we put negative 1 in the sign chart because it's a critical number. We put 1 in the sign chart because it's a critical number. We put 0 on the sign chart. It's not a critical number, but it's a place where the function doesn't exist. It's a place where we have a vertical asymptote. And so we look at our sign chart. When x is small, when it's very, very small, negative 3, negative 4, negative 6 trillion, we have a negative times a negative, which is positive, divided by x squared, which is positive. So we have positive numbers here. If x is between negative 1 and 0, this term is now positive. Positive times a negative divided by a positive is negative. X crosses over. It goes from between negative 1 and 0 to between 0 and 1. This does not change sign. The x squared does not change sign. So this term is still negative. This term is positive. So we have a positive times a negative divided by a positive, which is negative. As x crosses over 1, this term now becomes positive. So we have a positive times a positive divided by a positive, which is positive. So we look at our sign chart. Our function is decreasing from negative 1 to 0 and from 0 to 1. We put a square bracket around the negative 1, but not the 0. Our function's undefined at 0. So we do not include 0 in these intervals. It's increasing, negative infinity to negative 1, and 1 to infinity. And remember, the reason we can put the negative 1 here and here is because increasing and decreasing are properties that a function has over an interval, not at any one particular number. When your function goes from increasing to decreasing, that makes a local max. So our function went from increasing to decreasing at negative 1. That gave us a local max of negative 1 at negative 1. When your function goes from decreasing to increasing, that makes a local min. So we have a local min of 3 at 1, because 1 is where our function went from decreasing to increasing, that made a local min. Again, see the notes for the graph of the function. And we graphed this function in an earlier chapter, in an earlier video, and I said eventually when we get to the chapter on derivatives and graphs, we would see where the local min and the local max came from. So, well, we're here now, so now we know where that comes from. And again, see your notes for the graph of the function.